So the internet said that this could not be done running EG4 6000 XP inverters or any other Chinese inverter. That most of them have the same issue of Tesla Model S battery modules used off eBay, 300 bucks each, almost 4 kilowatt one battery module, completely off grid, not connected to outside power, running a workshop and also charging our Tesla Model S outside. Let me show you more about that. That is our Tesla Model S, happily charging, running off our EG4 6000 XP inverters, only using solar power, only what we have available in the sky. And the coolest thing is, it's currently at 17 amps here. I hope you can see that. And if the conditions in the sky change, a cloud moving in, the output or the charge current to the car will be reduced accordingly. And that is the really cool part I'm gonna show you now. So the car is connected to this OpenEVSE Arduino based open source charge controller. The display fell down, I have to fix that, but it's working fine. Don't worry about that. The problem with these units is they're expecting a signal of the inverter, grid export signal, in order to adjust the charging current to the vehicle. And the EG4 6000 inverters don't have that signal, and a lot of others as well, as far as I know, especially if they're not connected to the grid. This is a problem. So this is where my solution comes in. So we have a little solar panel here aimed at the sky, and that is providing a voltage signal to my home assistant setup, which is a little Arduino Raspberry Pi project. And with that we can calculate how much potential solar energy I can generate with my setup. And as soon as a cloud comes by and this gets shaded, the charge current in the vehicle will drop. And so that way I will never drain my battery modules on the wall. Let me show you. So our car is currently pulling that's the blue line, that's the car. Okay, shade. Dropping, I can hear the inverter going down. And now full sunshine again. Takes a bit. No. So that's how that works. Okay, maybe one more time. Shade. Dropping. Sunshine. Yeah, and with that, I keep my battery modules happy. Boom. Works flawless since years. Now, before I walk you through how my charge regulator based on sky conditions works, let me explain you how I set up these Tesla Model S battery modules as my house battery. These inverters, they usually expect to work with these battery cells. 16 of those. They are LFP, totally different chemistry than these Model S batteries, which are lithium ion cells, typical 18650 batteries, and this is actually out of a Model S. And you've all used these in your daily life. They're in battery, in flashlights and so on. Very good quality cell, so very good actually for home storage, but they have a different voltage range than these batteries here. So the nominal voltage of these is 3.5. That's what they are considered being full. And going up to 3.8 if they're really full, but usually 3.5 is the max. Going down to 3 volts, so the range is between 3 to 3.5. The normal, well, not even as low as 3 volts, maybe 3.2 to 3.5. But yeah, if really drained, they go down to 3 volts, and if really full, to 3.8 volts. And they have typically 16 of these in series, which brings us to roughly 60 of these cells at 3.8 volts, roughly 60 volts full, and going down to 48 volts when they're really empty. And that's what these inverters, the EG4 and most others, expect a voltage range between 48 to maximum 60 volts. And that's how they really happily communicate with the BMS and run the whole logic of making sure these cells, these individual cell packages, are not over or undercharged. It works just great. Yeah. The problem is our 18650 Tesla cells range between 3.2 volts if really empty, maybe also 3, but up to 4.2 if really full. And you can already tell that's a totally different range. And we can adapt to this based on how many we put in series behind of each other. One of these Model S battery modules that you can buy easily on eBay, really cheap, 300 bucks one piece. That's why this is so attractive. They have, like, when they are new, 4 kilowatts of energy, which is a really good deal, 300 bucks. But they feature 6 of these cells in packs of 78 in series. So if we take 6 times, let's say 4 volts, if we use this as our 100% range, that would be 24 volts full, right? And if we put 2 of these behind each other in series, we had 48 volts. And that, of course, 48 volts full, maybe up to, if we charge them to 4.2, what we don't want to do on a house battery because they're gonna wear down. It's like 100%. Then where are we then? 4.2 times 12, 50.4, which is still far too low for these inverters to work properly. Now if we want to just say, okay, we add a third one, then our voltage range is way too high. If we are at 12, so we have 18. If we use 3 of these, we have 18 cell packs times 4.2. We would be at 75 volts, and these things max out at 60. And that's the whole problem. The voltage range of these modules is not ideal. And that's something that is actually not so difficult to fix, I found out. Let me tell you how I did it. Now, before you guys light up my comment section, I have to admit, I know this is a total inappropriate Russian hack style build, and I have to tell you this was just temporarily to find out if this all works, okay? And that was 3 years ago. It has worked great since then, and now I'm planning to add another battery bank and package this all properly with the right wiring and the right termination, the right fastening method. Yes, I promise you. And so in case you want to see that build, make sure you subscribe to the channel and you like this video also. Again, this is just temporary, okay? The spider webs and the faded wires, time, you know, goes differently for everybody. So, yeah. Anyway, I'm in a isolated container here. There's no structures around it. The door, it's all steel and metal. The door can be closed. And if one of these batteries should really catch fire, the strap is gonna melt and it's gonna fall down into my freezer and melt through the ice cream. And that's the plan, okay? That's the safety concept. I'm just kidding. So again, the full build video is coming soon. I'm gonna put all of these modules into a metal enclosure that I already bought and wire everything up properly. This JK BMS here, my favorite brand, also has temperature sensors on each brick. You see one, here another one, here another one, and here one. So awesome setup. And yeah, now let me tell you how I solved this voltage issue. So we have one full module here, 6 modules, 24 volts fully, connecting to this one here, another full module, right? So we had 48 volts. Then it goes up to this one. But as you can see, this one here is not terminated at the end because I terminated the module right here. Okay, and that's also a Russian hack style solution, which I'm kind of shy to show you how that is done close up, but I still will right now. So this module here on top, again, we are going in here. We are tapping into the first brick and the second brick in series, but we pulled the power out of the second brick before it goes into the third brick over here. And I did that by just clamping a piece of aluminum. Let me remove the spider webs real quick. Clamping a piece of aluminum with a vice grip to this, you know, just to find out if it works. And it did. No overheating ever. Solid solution. I'm pulling maximum 60 amps. I don't need more, because especially now I'm gonna add another battery module. Yeah, and that's how I solved that. Surprisingly simple. Don't try this at home. This is not proper. So I'm touching this, you know, we have 50 volts here, 60. But no problem, for me at least. Don't try that at home, okay? I'm a trained professional. And from here it goes back into the inverter, right? Closing our loop, right? So the other end is here. We go through this pack, down here, 6 in series, up here, 1, 2 in series, and then we go back into the inverter. Now this battery module is actually one that is defect. It had, you can see here still the markings. Number 3 brick was broken, and that's why it was disposed. So I got this one for free even, and that's why this is such a sweet solution. So I'm using only 2 out of 6 bricks in this whole module here, and it was free of charge. So I basically only bought these 2 here at full eBay price, and this one was free. So that's how this works. So let me show you how this looks in our BMS. This is the app that comes with all the JK BMSs. So we are currently at 56 volts. A happy sweet spot for our BMS. Remember, for our inverter, remember the ideal voltage is 16 times 3.5 is 56. That's where we are right now. And each of our cells, you can see 1, 2, 3, 4, 5, counting up to 14, right? So again, one Model S module is 6 in series. 1, 2, it's this one and that one, and then our last two up here, these two are here, 1, 2, and that's how this thing has been running ever since. And you know what they say, right? Never change a running system. Just as a word of caution also, OSHA considers anything above 50 volts as hazardous. Okay, and we had 56 volts here, so that's why you should never ever touch this like I did. Now let me come to the charge controller real quick. This little solar panel I showed you before, the signal comes in here, coming to a little resistor. I forgot the ohms, but that's not really important. Maybe I can still read it here. No. And then the voltage, otherwise the voltage would be too high for my system, goes into this Shelly Uni Plus, which is an awesome device, and that is connected to Wi-Fi and sends a voltage signal to Home Assistant. I'm gonna show you right now how that looks like. Okay, this is my Home Assistant setup. Cool little open source project running on a Raspberry Pi, and if there's enough interest for how this all works, I'm gonna make another video. Let me know in the comments. I now just gonna briefly show you how I did that charge controller. So this here is the data feed of my inverter, the EG4. It shows up as lux power here because that's just the same unit, same hardware, typical Chinese thing. So this lux power SNA is the same as the 4G 6000 XP, and it has all sorts of data points. So let me see here, PV voltages, grid frequency. Obviously we are not connected to the grid. It's showing our battery, for example, here. This is the Tesla battery rig, and oh yeah, that's quite interesting here. You can see the voltage. So this is yesterday evening when it was full, right? And at 8 o'clock, and since then it was dropping to 54 volts at 6 in the morning. And then solar kicked in and charged it up, and here it was dropping again because I was playing with this when I showed you how this little solar panel works to control the charge current. So it was buffering with the battery, and it sucked it down a little bit, and then it started charging up again. So yeah, that's the data feed we have in here. But again, this inverter does not generate the so-called grid export, which usually is the figure we could use to communicate with this OpenEVSE charge controller. And that's why we are reading here the voltage. That's the little panel I showed you. That's the little solar panel that has the two wires going down to the Shelly Uni Plus, and it also has a temperature sensor, which is kind of cool. So here we can see the voltage history. See here, same thing, 6:30 in the morning. Obviously it was dark, right? And then sun came up, the voltage increased, and that curve is basically the capacity I have with those solar panels. And those two dips here is when I showed you, when I covered this panel partially, that's when the voltage dropped, and that's when the charge controller reduced the current going to the car. Yeah, and that's how that works. Quite simple, right? Took me a while to figure this out, but it works flawless. So I have a formula running behind. Again, I can dive into that if anyone is interested. I'm not sure there's any real interest. For now, I just want to show you guys how this is done. And that the signal is going into OpenEVSE from Home Assistant into here. This is all done through MQTT, which is a really cool protocol coming from the gas industry, gas and oil industry. Super cool. I'm so glad I learned this. When we go into self-production here, we can, yeah. So this export value is what I calculate with that little solar panel. That's usually what this OpenEVSE is expecting to see from the inverter, the export value. And out of that, it can calculate the charge current. And you can see it's much lower already because the sun is going down right now. It's gonna drop. As soon as it's below 5, the charging will automatically stop. Okay. And yeah, you can see now the car is at 8 amps here. And it's gonna go down from now on. So it's fully automated. Never had a problem with this. Really works cool. Short update. The sun is much lower now, and our charge wattage is about 2000 watts. Before, like 2 hours ago, it was 3.5, and I expect like in 1 or 2 hours from now it's gonna shut off. And that's, yeah, all automatically controlled. Pretty sweet, right? Sun lower again. We had only 1400 watts, 5 amps here, so it's gonna switch off very soon. I try to catch this moment when it clicks off. It just happened. Just turned off. You can see it's 0 now. Like 30 seconds after I stopped the video, the battery is getting some more juice because obviously we still have capacity. The sun is still out, but much lower, and that is going into our battery bank and not the car anymore. So really a fully automated system. And this load here is the light in my workshop, the 300 and something watts. Yeah. If you want to be with me when I'm building the second battery bank, and I already have the JK BMS here for that, my second JK BMS. Yeah, I'm gonna create a video where I share how to hook this up and program it, also how to get the charge controller working, and most important of all, how to package all this properly in a nice metal enclosure. So like and subscribe, and I hope to see you soon.